Welcome back, Night Wanderer. Tonight, we're exploring one of the universe's most elegant impossibilities. White holes, the cosmic mirrors that exist perfectly in mathematics, but seem to refuse existence in reality. If you're enjoying these journeys through the cosmos, a like helps others find their way here, and subscribing means we can drift through the universe together more often. And if there's a corner of science you'd like to explore on a future night, leave it in the comments. I read every single one. Now, let's begin. White holes are the theoretical opposite of black holes. Instead of pulling everything in, they would push everything out. Imagine for a moment a fountain in the centre of a town square. Water flows upward and outward, cascading down in all directions, and no matter how you tried, you couldn't pour a cup of water back into that central spout. The fountain only gives, never receives. White holes work on this principle, but instead of water, they fountain forth matter, energy, light itself. Everything that exists, pouring outward from a single point in space-time. Black holes have become almost familiar to us now, haven't they? We've seen their shadows photographed, watched stars orbit invisible points of crushing gravity, felt a certain comfort in understanding, or thinking we understand, these cosmic vacuum cleaners. But white holes flip that script entirely. Where a black hole's event horizon is a one-way door inward, a point of no return where everything falls toward an inescapable centre, a white hole's horizon works in reverse. It's a boundary you can exit but never enter, no matter how much fuel you burned, no matter how determined you were. Think about what that means for a moment. Every object you've ever encountered can be approached, touched, entered if it has an interior. You can walk into a building, dive into an ocean, burrow into soil. But a white hole defies this basic expectation of reality. You could accelerate toward it at nearly the speed of light, and the universe would simply reject you. Not through force in the traditional sense, but through the geometry of space-time itself, which curves in such a way that all paths lead away, never toward. It's enough to make you reconsider what we mean by place, or object, at all. Perhaps that's why they've never been found. The universe, it seems, has opinions about what should and shouldn't exist, and white holes fall firmly into the latter category, at least in the cosmos we inhabit now. White holes are predicted by the same equations that describe black holes, just running in reverse through time. Einstein's field equations, those 10 interlinked mathematical expressions that describe how matter and energy curve spacetime, have a peculiar feature. They don't care which direction time flows. You can plug in values for a black hole, watch how spacetime bends inward toward a crushing singularity, and then, almost like rewinding a film, run those same equations backward. What emerges is the white hole, identical in structure but inverted in behaviour. This mathematical time reversal symmetry is both beautiful and troubling. Beautiful because it reveals a deep elegance in the laws of physics, a suggestion that the universe operates according to principles more fundamental than our everyday experience of cause and effect. Troubling because our universe clearly does have a preferred direction for time. Your coffee cools, never spontaneously heats. Eggs scramble but don't unscramble. Entropy increases. And yet, Einstein's equations suggest that for every black hole pulling time forward toward an inevitable singularity, there could be a white hole pushing time backward, ejecting matter from a past that never quite reaches us. Physicists call this the time reversal symmetry of general relativity, and it's one of those aspects of mathematics that makes you wonder whether the equations are revealing deep truths about reality or simply exploring all logical possibilities, whether or not nature bothers to implement them. It's a bit like discovering that the blueprint for a building includes detailed plans for an upside-down version in the basement, perfectly valid according to architectural principles, but never actually constructed. Maybe that's what white holes are, perfectly valid solutions that nature looked at and said, "No, thank you, that's not how this universe operates." No white hole has ever been observed in the universe, making them purely theoretical objects. We've mapped the cosmic microwave background, the afterglow of the Big Bang itself. We've detected gravitational waves from colliding black holes billions of light years away. We've photographed the shadows of supermassive black holes at galactic centres, capturing the unseeable. We've found exoplanets, measured dark energy, traced the large-scale structure of the universe across billions of years. And in all that observation, Across all those telescopes and detectors and careful measurements, we've never found even a hint of a white hole. They exist in a strange category of scientific objects, things that should be possible according to our best theories, but apparently aren't actual. It's not that we've looked and found evidence against them exactly. It's more that the universe has given us every other prediction from general relativity. The bending of starlight, the precession of Mercury's orbit, gravitational waves, black holes themselves, but has remained conspicuously silent on this one. There's something almost poignant about it, isn't there? These objects living perfectly in the mathematics, encoded in the same equations that describe confirmed phenomena, and yet remaining forever absent from reality. They're ghosts in the machinery of space-time, theoretical possibilities that haunt the edges of physics papers but never materialize under the gaze of our instruments. Some physicists spend entire careers studying them, not because they expect to find one, but because understanding why they don't exist might teach us something profound about why anything exists at all. Perhaps that's enough. Perhaps some truths about the universe reveal themselves not through what is, but through what conspicuously isn't. The event horizon of a white hole works opposite to a black hole's. It's a boundary you can exit but never enter. Event horizons are strange beasts. The term itself is beautifully chosen. It's the horizon beyond which events become forever hidden from view, a cosmic veil that separates the knowable from the unknowable. For a black hole, this horizon marks the point where escape velocity exceeds the speed of light. Cross it, and every possible path through spacetime leads inward, toward the singularity. There is no trajectory, no amount of thrust, no clever maneuver that leads back out. The future itself points only toward the centre, but a white hole's horizon inverts this geometry. Here, every possible path leads outward. You could witness matter and light erupting from this boundary, streaming away into the cosmos, but you could never send a probe inward to investigate its source, fire a rocket at it, and the rocket would find itself deflected, pushed back. Not by a force in the conventional sense, but by the shape of space-time itself. It's as if the universe has constructed a one-way mirror in reverse. You can leave, but never arrive. Try to imagine encountering such a thing. You're piloting a spacecraft, approaching what appears to be a bright, energetic object. You fire your engines to slow down, to enter orbit, perhaps to investigate. But as you draw closer, something impossible happens. Your trajectory curves away despite your engines. You add more thrust, pointing yourself directly at the object, and still you find yourself deflected, pushed along paths that lead anywhere but there. The harder you try to approach, the more forcefully spacetime guides you elsewhere. It would be maddening in a way, wouldn't it? To see something, to observe it clearly, to watch matter streaming out from it, and yet to be forever denied access, not through any barrier you could break or force you could overcome, but through the fundamental geometry of reality itself. Some boundaries, it seems, are woven into the fabric of existence. Some physicists believe white holes might have existed only in the first moments after the Big Bang. The early universe was a strange place, or perhaps place isn't quite the right word for something that was everywhere at once, a roiling sea of energy so dense and hot that matter as we know it couldn't exist yet. In those first fractions of a second after the Big Bang, the laws of physics operated at extremes we can barely simulate even with our most powerful computers. Time itself behaved differently. Space expanded faster than light. Quantum fluctuations got stretched to cosmic scales, becoming the seeds of galaxies, and perhaps in that chaos white holes briefly existed. If they were ever going to form naturally, it would have been then, in those wild moments before the universe settled into the calmer, more orderly state we inhabit now. Some theories suggest that the extreme conditions of the early universe, the intense densities, the violent fluctuations in space-time, might have allowed white holes to appear as cosmic relics, echoes of creation itself. But if they existed at all, they didn't last. The same instabilities that would destroy a white hole in our current universe would have operated even more intensely back then. Perhaps they evaporated in the cosmic microwave background, their energy scattered so thoroughly that we'd never detect them now. Perhaps they transformed into something else entirely, black holes, maybe, or ordinary matter, or simply dissipated into radiation and entropy. It's a melancholy thought, in a way. The idea that the universe might have been briefly populated by these impossible objects, fountains of matter erupting in all directions, only to vanish before stars formed, before galaxies coalesced, before anyone could be there to witness them. Like fireworks at a celebration attended by no one, beautiful and brief, and forever unrecorded. A white hole would appear incredibly bright, constantly ejecting matter and radiation into space. Picture the brightest thing you've ever seen. Maybe it was the sun glinting off snow, forcing you to squint and look away. Maybe it was a welding torch, that blue-white point of light that burns after images into your vision. Maybe it was lightning splitting the night sky, turning darkness to daylight for a fraction of a second. Now imagine something brighter than all of these, not just brighter, but fundamentally, constantly, impossibly radiant. A white hole wouldn't just emit light. It would be a cosmic beacon, a fountain of photons streaming outward in all directions, never diminishing, never resting. Unlike a star, which shines because of nuclear fusion in its core, a white hole would glow because of its very nature, matter and energy erupting from its event horizon, ejected by the geometry of spacetime itself. Every wavelength would be present: radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. The entire electromagnetic spectrum pouring forth in an endless cascade. And it wouldn't just be light. Matter would fountain outward too. Elementary particles, atoms, perhaps even larger structures, all racing away from that impossible boundary at tremendous speeds. If you could somehow observe a white hole from a safe distance, though safe might be a relative term when dealing with such an object, you'd see something like a cosmic geyser, brilliant and relentless, visible across vast stretches of space. This brightness is actually one reason we can be fairly confident. White holes don't populate our universe, at least not in any significant numbers, something that luminous would be hard to miss. Our telescopes scan the sky continuously, cataloguing objects, measuring their spectra, tracking their behavior over time. An object constantly ejecting matter and radiation would stand out like a lighthouse in the dark, and yet we see nothing that fits this description. The universe is full of bright objects, quasars, gamma-ray bursts, supernovae, but none behave quite like a white hole should. The silence is telling. The interior of a white hole would be completely inaccessible to any observer in our universe. There's a particular kind of frustration that comes from knowing something exists but being unable to examine it. Archaeologists feel it when they discover a sealed tomb, but lack the tools to open it safely. Historians feel it when they learn of lost texts, burned libraries, knowledge that existed once but is now beyond recovery. But the inaccessibility of a white hole's interior is more absolute than any of these. It's not a practical barrier that better technology might overcome. It's a fundamental severing, written into the structure of space-time itself. The interior of a white hole is causally disconnected from our universe. That's a phrase that sounds technical but carries profound implications. It means that nothing happening inside can affect anything outside. No signal can travel from there to here. No information can leak across that boundary. It's not just hidden, it's fundamentally separate, existing in a region of space-time that branches away from our own. Like a stream splitting around a rock, the waters never mixing again. Think about what that means for the concept of knowledge. We're used to the idea that anything real can, in principle, be studied. Maybe not easily, maybe not with current technology, but eventually, given enough time and ingenuity, we could investigate it. The bottom of the ocean was once unreachable. Then we built submarines. The surface of Mars was once untouchable. Then we landed rovers. The interior of atoms was once invisible, then we developed particle accelerators. But the interior of a white hole? No amount of technological advancement would grant access. The barrier isn't technological, it's ontological. It's a bit like being told there's an entire universe just beyond a door, but the door only opens outward, never inward. You can watch things emerge, see them carrying evidence of wherever they came from, but you can never go there yourself, never verify, never explore. Some mysteries, it seems, are designed to remain mysteries forever, not because we lack curiosity or capability, but because reality itself has drawn a line and said, this far and no farther. Some theories suggest our entire universe might be the interior of a white hole from a parent universe. What if everything you've ever known, every star, every galaxy, every atom in your body, exists inside a white hole? It's one of those ideas that sounds like science fiction but emerges naturally from the mathematics of general relativity, one of those places where the equations lead if you follow them faithfully, without prejudging where they should go. The idea works like this. Imagine a black hole forming in some parent universe, matter collapsing under its own gravity. But instead of collapsing all the way to a singularity, quantum effects intervene at incredibly small scales, and the collapsing matter bounces, creating a new region of spacetime that expands rapidly. To observers in the parent universe, this remains hidden inside the black hole, causally disconnected. But to observers inside, us perhaps, this expanding region looks like a big bang, the birth of a universe. The mathematics of this scenario bear striking similarities to what we observe. The Big Bang was an explosive expansion from an incredibly dense hot state. Matter and energy streaming outward, space-time itself expanding, carrying galaxies along with it. And a white hole, by definition, is a region from which matter and energy erupt outward, unable to fall back in. The parallels are suggestive, maybe even compelling. Of course, this is deeply speculative. We have no way to test whether our universe is embedded in some larger structure, no method to peek outside and verify. We're like characters in a novel wondering whether they exist in a book, inhabitants of a system trying to understand the system from within. Maybe it's true. Maybe our Big Bang was the interior of a white hole, and we live in a cosmic bubble, forever separated from whatever reality spawned us. Or maybe the similarities are coincidental, the universe's way of using similar mathematical structures for unrelated phenomena. Either way, it's a humbling thought, isn't it? The possibility that everything might be nested inside something else. Turtles all the way down, or all the way up. White holes are mathematically unstable, meaning they would quickly decay or transform if they tried to form. Stability is something we take for granted in everyday objects. A chair stays a chair. A mountain remains a mountain, at least on timescales that matter to us. Even dynamic systems like stars achieve equilibrium, balancing the inward crush of gravity against the outward pressure of fusion, sometimes for billions of years. But white holes lack this quality entirely. They're mathematically unstable in a profound way, meaning that even the slightest perturbation, a single particle of matter, a stray photon, the quantum fluctuations inherent in spacetime itself, would cause them to collapse, transform, or simply cease to exist as white holes. Physicists who study these objects using computer simulations have found this again and again. You can set up the initial conditions carefully, create a white hole in the mathematical universe of the simulation, and then watch what happens. And what happens is that it doesn't last. The stability that allows black holes to persist for timescales longer than the current age of the universe simply doesn't extend to their time-reversed counterparts. It's as if nature has built a preference into the laws of physics, a subtle bias toward one direction of time over the other. Part of this instability stems from thermodynamics. The second law, that entropy, disorder, tends to increase, isn't just a statistical tendency. It's one of the most ironclad principles in physics, observed in every system we've ever studied, and a white hole, by its very nature, would seem to violate this law. It creates order from disorder, organizing matter and ejecting it outward rather than allowing it to diffuse and randomize. The universe, it seems, doesn't tolerate this behavior for long. So even if conditions somehow conspire to create a white hole, perhaps in the chaotic early universe, perhaps through some quantum fluctuation we haven't imagined, it wouldn't survive. It would be a fleeting thing, existing for perhaps the briefest instant before transforming into something more stable, more in line with how time actually flows in our universe. Nature, it seems, has strong opinions about what's allowed to persist, and white holes aren't on the approved list. Time works strangely at a white hole's horizon. External observers would see ejected matter frozen in time, stuck at the boundary. Time is supposed to be simple, isn't it? A steady tick, 1 second after another, the background against which everything else happens. But near horizons, whether black or white, time reveals itself as something far stranger, something that can stretch and compress, slow to a crawl or race ahead, depending on where you're standing and what you're observing. For a white hole, this temporal strangeness manifests in a peculiar way. Imagine you're watching from a safe distance as matter erupts from the white hole's horizon, you'd expect to see it emerging cleanly, streaming away into space. But that's not quite what you'd observe. Instead, matter at the very edge of the horizon would appear to slow down, redshifted by the extreme gravitational effects, its light stretched to longer and longer wavelengths. Material just emerging would seem frozen, stuck at the boundary, asymptotically approaching but never quite leaving, even though from the matter's own perspective, it's streaming away perfectly normally. This is the mirror image of what happens at a black hole's event horizon. There, in falling matter appears frozen from an outside perspective, time slowing to a stop as the material approaches the point of no return. The mathematics is identical, just reversed. Another instance of that time reversal symmetry that permits white holes to exist on paper while nature declines to implement them in reality. What creates this temporal freezing? It's the extreme curvature of spacetime near the horizon. Time is not absolute, it's relative, flowing at different rates depending on the gravitational field you're in. Near a horizon, the gravitational time dilation becomes so extreme that time, as measured by a distant observer, effectively stops. Light from that region takes longer and longer to reach you, red-shifted to invisibility, carrying information about events that seem to unfold in slow motion, then slower, then not at all. It's enough to make you reconsider what we mean by now. If time flows differently at different locations, if what seems frozen to you is moving normally from another perspective, then simultaneity, the idea of events happening at the same time, becomes slippery, dependent on your frame of reference. Maybe time isn't the simple backdrop we imagine, but something more fluid, more negotiable, shaped by gravity and motion into forms we're only beginning to understand. If you could somehow approach a white hole, the forces would push you away with increasing strength. There's something deeply unsettling about the idea of being pushed away by nothing. We're used to forces we can understand: wind against your face, a hand on your shoulder, the repulsion of magnets held pole to pole. These are forces with sources, with mechanisms, with explanations that make intuitive sense. But a white hole would reject you through geometry alone, through the shape of spacetime itself, curving in such a way that all possible paths lead away from the center. Imagine piloting a spacecraft toward one. At first, from a great distance, nothing seems unusual. You fire your engines, accelerate, watch the object grow brighter in your view screen. But as you draw closer, you begin to notice something strange. Despite your velocity, despite the thrust of your engines, you don't seem to be getting much closer. You check your instruments. Everything's functioning normally. You increase power, and yet the white hole remains stubbornly distant, as if you're walking toward a horizon that retreats as fast as you approach. Push harder, and the effect intensifies. The space-time around you is curved so severely that your trajectory, no matter how you orient it, bends away. It's not that you're being repelled by some force field or pressure wave. It's that forward, in the direction of the white hole, has ceased to be a direction you can travel. The geometry has closed that option, the same way you can't walk north from the North Pole. There simply isn't a north to walk toward once you're there. And if you somehow managed to get close enough, the effects would become violent. The curvature of space-time would create tidal forces, stretching you in some directions while compressing you in others. Just like falling into a black hole would spaghettify you, stretching you into a long, thin strand. Approaching a white hole would subject you to similar stresses, pulling and pushing as the geometry fought against your presence. Perhaps this is nature's way of protecting the boundary, ensuring that the mathematical impossibility remains just that: impossible, unapproachable, forever theoretical. Some places, it seems, aren't meant to be visited, not because they're dangerous in the usual sense, but because they exist in configurations of space-time that fundamentally exclude the possibility of arrival. The concept of white holes was first explored seriously in the 1960s by Soviet physicist Igor Novikov. Sometimes the most profound discoveries come not from looking at new things, but from looking at familiar things in new ways. Igor Novikov, working in the Soviet Union during the height of the Cold War, did exactly this with the equations describing black holes. He asked a simple question: what happens if you run the mathematics backward? It was the 1960s, a time when black holes themselves were still controversial, still being argued about in physics journals and conference halls. Many physicists thought they were mathematical curiosities that couldn't exist in nature, solutions to Einstein's equations that were too extreme, too bizarre to be real. Novikov was working in this uncertain landscape, exploring the implications of general relativity without knowing which solutions nature had actually implemented. When he followed the mathematics backward through time, what emerged was the white hole, a mirror image of the black hole identical in structure but opposite in behaviour. It was an elegant result, the kind of mathematical symmetry that makes physicists sit up and take notice. If the equations permitted black holes, they also permitted white holes. The laws of physics, as written, didn't distinguish between the two. Of course, Novikov didn't claim to have discovered a real object out in the universe. He was careful, methodical, exploring what the mathematics allowed, without making claims about what nature had chosen. But his work opened up a whole avenue of theoretical exploration. Other physicists began studying white holes, probing their properties, investigating whether there were any circumstances under which they might form. It's interesting, isn't it, how theoretical physics sometimes works. Someone sits down with equations, follows them faithfully wherever they lead, and discovers entire classes of objects that may or may not exist. It's a bit like an explorer mapping territories that might be purely imaginary, charting coastlines and mountain ranges in worlds that could be fiction. And yet, sometimes those maps turn out to describe reality. Black holes themselves were once considered purely theoretical, and now we've photographed them. White holes might be different, or perhaps we just haven't looked in the right way yet. A white hole cannot form from the collapse of matter like a black hole does. Black holes have an origin story we can understand, at least in broad strokes. A massive star exhausts its fuel, fusion stops, and without the outward pressure of nuclear reactions to balance gravity's inward pull, the core collapses. If the star is massive enough, this collapse doesn't stop at any intermediate stage. Not a white dwarf, not a neutron star, but complete gravitational collapse, creating a black hole. It's a process we can model, simulate, and in some cases, observe directly as supernovae light up across the cosmos. But white holes have no such origin story. There's no process, no sequence of events, no physical mechanism that would create one from ordinary matter. You can't take a star and make it uncollapse. You can't gather matter together and have it spontaneously form a boundary that ejects everything rather than attracting it. The arrow of time, the directionality of cause and effect, the increase of entropy, all of these conspire to prevent white holes from forming through any natural process. This is one of the deepest asymmetries in physics. Black holes form from futures, from matter collapsing forward through time toward an inevitable singularity. White holes, if they exist at all, would have to emerge from pasts, from initial conditions set at the beginning of the universe, or from quantum fluctuations that somehow circumvent the normal flow of causality. They can't be created. They can only have always been there, primordial relics or quantum anomalies, not the end result of any process we can point to and understand. It makes you wonder about the nature of time itself. Why can matter collapse, but not uncollapse? Why does entropy increase but never decrease spontaneously on large scales? These questions sound simple, but they cut to the heart of why the universe behaves the way it does. Physics equations often permit time reversal, run them backward, and you get valid solutions. But the universe itself clearly has a preference. It ages in one direction, evolves forward, never backward. Maybe white holes are the price of that preference. Maybe they're the roads not taken, the possibilities the universe examined and rejected. Or maybe they're hints of something deeper, some principle we haven't discovered yet that explains why nature chooses the solutions it does and leaves others as beautiful, unrealized mathematics. Some researchers propose that white holes might be connected to black holes through wormholes called Einstein-Rosen bridges. Here's an idea that captures the imagination. What falls into a black hole might not be destroyed. Instead, it might traverse a tunnel through spacetime, a wormhole, formerly called an Einstein-Rosen bridge, and emerge from a white hole somewhere or somewhere else. Matter goes in here, comes out there, a cosmic transit system connecting distant regions of the universe, or even different universes altogether. The mathematics allows this in a limited sense. When Einstein and Nathan Rosen first explored the solutions to general relativity, they found that the geometry describing a black hole could be extended to include another region, a mirror image on the other side of the spacetime diagram. This other region had all the properties of a white hole, a boundary that could be exited but not entered. And connecting the two was a throat, a narrow passage through which, in principle, matter and light could travel. But, and this is a significant but, the mathematics that permits this connection also reveals a fatal flaw. The wormhole is unstable. It exists for only an instant, collapsing so quickly that not even light could traverse it before the throat pinches off. Any matter trying to make the journey would be crushed in the collapse, unable to complete the transit from black hole to white hole. It's like discovering a tunnel between two cities but finding that the tunnel collapses the moment you enter it. Some physicists have explored whether exotic matter, stuff with negative energy density, allowed by quantum mechanics but never observed in bulk, might hold the wormhole open, propping up the throat like scaffolding supporting a tunnel. If such matter existed and could be arranged correctly, maybe the connection could be stabilized, made traversable. But this remains deeply speculative, edging into science fiction territory even as it stays within the bounds of mathematical possibility. Still, the idea persists, doesn't it? The notion that black holes might not be endpoints but gateways, that the matter falling into them might re-emerge somewhere else, fountaining out of white holes in distant corners of space-time. It's a beautiful thought, even if nature hasn't implemented it. Perhaps beauty and truth don't always align, and we have to content ourselves with knowing what could be, even if it isn't what is. The Penrose diagram, a map of space-time, shows white holes as mirror regions to black holes. Sometimes understanding requires a new kind of map. You can't navigate curved space-time using ordinary coordinates the way you'd use latitude and longitude to navigate Earth's surface. The curvature is too severe, the distortion's too extreme. So physicists developed a different kind of cartography, and one of the most powerful tools is the Penrose diagram, named after Roger Penrose, who invented this method of compressing infinite spacetimes onto finite pages. A Penrose diagram for a black hole reveals something remarkable. The familiar event horizon appears as a diagonal line, separating the exterior universe from the interior. Time runs upward on the page, and future-directed paths, the world lines of particles and light rays, always slope upward, never backward. Follow these lines into the black hole, and they inevitably reach the singularity at the top of the diagram, a jagged line representing the place where space-time curves infinitely and physics breaks down. But the diagram doesn't end there. If you extend it, following the mathematics to its logical conclusion, another region appears on the left side of the diagram, a mirror image of the black hole. This region has a diagonal boundary too, but this one can be crossed only from inside to outside, never the reverse. It's the white hole, geometrically identical to the black hole but inverted in time. The singularity extends to the past instead of the future, a boundary not of endings but of beginnings. Looking at a Penrose diagram is a bit like seeing the hidden architecture of space-time, the scaffolding that holds reality together. These diagrams reveal symmetries that aren't obvious when you're just working with equations or trying to visualize in ordinary space. They show how black holes and white holes are related, two sides of the same geometric coin, separated not by distance but by the direction of time's arrow. Of course, just because the diagram includes both regions doesn't mean both exist in our universe. The Penrose diagram shows what's mathematically possible, the complete solution space. Nature, as usual, appears to have selected only part of this space, the black hole side, and left the white hole side as a beautiful but unrealized abstraction. Still, these diagrams help us think about what could be, and sometimes understanding what could be is the first step toward understanding what is. A white hole would violate the second law of thermodynamics, which says disorder should always increase. Entropy is one of those concepts that sounds abstract until you realize it's everywhere around you. It's why ice melts in warm water, but warm water never spontaneously freezes. It's why perfume disperses through a room but never gathers back into the bottle. It's why broken eggs don't reassemble themselves, why mixed paint doesn't unmix, why the universe as a whole tends toward greater disorder, greater randomness, greater chaos as time marches forward. The second law of thermodynamics codifies this observation. In any closed system, entropy, this measure of disorder, never decreases. It might stay the same in idealized reversible processes, but in reality it always increases. Heat flows from hot to cold, never the reverse. Energy spreads out, diffuses, becomes less useful for doing work. It's one of the most ironclad principles in all of physics, observed in every system ever studied, from coffee cooling in a cup to the heat death predicted for the entire universe billions of years hence. And white holes would seem to violate this principle fundamentally. Imagine matter erupting from a white hole's horizon, particles streaming outward in organized flows, energy concentrated and directed rather than diffused and random. Where did this organization come from? What source is decreasing its entropy to allow this outflow of order? In a normal system, creating such organized motion requires work, requires some other part of the system to increase its entropy even more. But a white hole has no other part, it just is spontaneously ejecting matter in defiance of thermodynamics' stern commandments. This might be the deepest reason white holes don't exist in our universe. The laws of thermodynamics aren't suggestions. They're among the most fundamental constraints on what's physically possible. You can bend them in small systems for brief moments through quantum fluctuations, but macroscopically over time they always win. A white hole would represent a sustained, large-scale violation, a cosmic fountain of decreasing entropy, and the universe simply doesn't allow that. Perhaps this is why black holes persist while white holes don't. Black holes are thermodynamically permissible, even thermodynamically favourable. They increase the universe's entropy by taking ordered matter and crushing it beyond recognition. White holes would do the opposite, and nature seems to have built-in mechanisms that prevent or destroy anything attempting such thermodynamic heresy. Order decreases, chaos increases, the universe ages in one direction, and white holes, beautiful as they are mathematically, stand on the wrong side of this cosmic law. Some cosmologists suggest white holes might explain mysterious gamma-ray bursts we detect from space. Every now and then, our detectors light up with something extraordinary. A brief, intense flash of gamma rays, the most energetic form of light in the electromagnetic spectrum, arriving from some distant point in the universe. These gamma-ray bursts are among the most luminous events we observe, briefly outshining entire galaxies, releasing in seconds as much energy as our Sun will produce over its entire 10 billion year lifetime. And while we've developed explanations for many of them, colliding neutron stars, certain types of supernovae, some remain mysterious, their origins unclear. Could white holes be responsible for some of these bursts? It's a speculative idea, but not entirely without merit. If a white hole were to form even briefly, it would eject matter and energy violently, in all wavelengths, including gamma rays. The sudden appearance and equally sudden disappearance of such an object might produce exactly the kind of brief, intense signal we observe. And because white holes would be unstable, existing only momentarily before transforming or evaporating, we'd never see them in follow-up observations, just the flash, then nothing, exactly what we observe with some gamma-ray bursts. Of course, this explanation faces significant challenges. We have other, more conventional explanations for most bursts, explanations that don't require invoking exotic objects that we've never confirmed exist. Occam's razor suggests we should prefer these simpler explanations until we have evidence demanding something more exotic, and the evidence for white holes remains non-existent outside of mathematics. But gamma-ray bursts are genuinely mysterious phenomena, coming from distances so vast that we're seeing events that happened billions of years ago in cosmic environments we can barely imagine. Some are associated with supernovae or galaxy mergers, but others appear in empty regions of space with no obvious source. Perhaps a few of these, the ones that don't fit our models, the ones that remain stubbornly unexplained, might be evidence of something stranger. Or perhaps they're just phenomena we haven't understood yet through conventional physics. The universe is full of energetic processes, and our knowledge remains incomplete. Still, it's worth considering the exotic possibilities alongside the mundane ones, if only to ensure we're not missing something profound hiding in plain sight, disguised as just another flash of light from the deep cosmos. The white hole solution appears when you solve Einstein's equations for a non-rotating uncharged black hole. Mathematics has a way of offering more than you ask for. When Karl Schwarzschild, just months after Einstein published his theory of general relativity, sat down to find an exact solution to the field equations, a precise description of how spacetime curves around a massive object, he was looking for something practical, something that might describe the gravitational field outside a star. What he found was both more and less than that. The Schwarzschild solution, as it came to be known, described what we now recognise as a black hole, though that term wouldn't be coined for another 50 years. But embedded in the same mathematics, appearing naturally when you extend the solution to its full extent, was the white hole, a region of spacetime with properties mirror opposite to the black hole. Schwarzschild probably didn't think much of this extra region. It seemed like a mathematical artifact, an excess solution that the equations coughed up alongside the physically relevant one. And he wasn't entirely wrong to think that way. The white hole solution emerges from taking the mathematics seriously, following it wherever it leads without imposing additional constraints like, this must match the collapse of a physical star, or this must respect causality as we experience it. Pure mathematics doesn't care about physical plausibility. It explores all logical possibilities, whether or not nature implements them. This is one of the strange aspects of theoretical physics. The equations often describe more than exists. Maxwell's equations allow electromagnetic waves, which turned out to be real. We call them light, radio waves, X-rays. But they also permit solutions that seem unphysical, like waves with infinite energy, or fields that extend infinitely into the past. Einstein's equations allow black holes, which turned out to be real, but also white holes, which haven't. The mathematics casts a wider net than reality fills. Perhaps that's appropriate. Mathematics is the language of possibility, while physics is the science of actuality. Not every grammatically correct sentence is true, and not every mathematically valid solution corresponds to something real. But studying the full range of solutions, even the unphysical ones, teaches us about the structure of the theory, about what constraints we need to impose to select the universe we actually inhabit from the larger space of mathematical possibility. If white holes existed, they couldn't last long. Quantum effects would likely destroy them almost immediately. Even setting aside the instability that classical general relativity predicts for white holes, quantum mechanics delivers another blow to their prospects for existence. At small scales, at high energies, quantum effects become important, and spacetime itself begins to fluctuate, to foam and bubble in ways that classical physics never anticipated. And these quantum fluctuations, it turns out, would likely destroy a white hole almost as soon as it formed. The mechanism works something like this. Quantum mechanics permits the temporary creation of particle-antiparticle pairs from vacuum, virtual particles that pop into existence, exist briefly, then annihilate back into nothing. Near the event horizon of a white hole, these quantum fluctuations would be amplified by the extreme curvature of spacetime. Some of these particles would fall into the white hole, or rather, fail to fall in given the geometry, while others would escape, carrying energy away. But here's where it gets interesting. For a black hole, this process, Hawking radiation, causes the black hole to slowly evaporate over immense timescales. For a white hole, the geometry is inverted, and the quantum effects become even more disruptive. Instead of slow evaporation, you'd likely get rapid destabilization, the quantum foam eating away at the structure of the horizon until the white hole could no longer maintain its identity as a distinct object. Some physicists have run calculations suggesting that quantum effects would destroy a white hole in a fraction of a second, perhaps faster. The exact timescale depends on the white hole's mass and on details of quantum gravity that we don't fully understand yet, but the conclusion remains robust. Quantum mechanics and white holes don't get along. One destroys the other. It's another example of how nature uses multiple mechanisms to enforce consistency. Classical instability would destroy white holes on its own. Thermodynamic considerations argue against them. And now quantum mechanics adds a third veto, a third reason why these objects can exist in equations but not in reality. The universe, it seems, really doesn't want white holes to exist, and it's deployed every tool at its disposal to ensure they don't. A white hole's gravity would still pull on distant objects, even while forcefully ejecting nearby matter. Gravity is strange, and it becomes stranger still when you consider objects like white holes. From far away, say, from a distance of several light years, a white hole would look, gravitationally speaking, identical to a black hole of the same mass. Its gravity would pull on planets, bend the paths of passing spacecraft, curve light from distant stars in gravitational lensing. You couldn't tell, just from observing these gravitational effects, whether you were looking at a black hole or a white hole. This seems contradictory at first, doesn't it? How can an object that forcefully ejects everything nearby still gravitationally attract distant objects? The answer lies in understanding what gravity is in Einstein's framework. It's not a force, exactly, but a curvature of space-time. Mass warps the fabric of space and time, and objects move along the straightest paths they can find through this warped geometry. We perceive these curved paths as gravitational attraction. The white hole warps space-time just like any massive object does. From a distance, this warping creates the familiar effects of gravity, attraction, orbital motion, all the phenomena we associate with gravitational fields. But close to the horizon, the geometry becomes so extreme, so severely curved, that the nature of the warping changes. The paths through space-time become constrained in strange ways. Inward paths become impossible. Outward paths become mandatory. It's a bit like water near a drain. Far from the drain, water might flow in many directions, respond to various influences. But very close to the drain, the flow becomes directional, constrained by the geometry of the drain and the water's motion. White holes work similarly, though the drainage flows outward rather than inward, and the medium being drained is space-time itself rather than water. So you could, in principle, orbit a white hole from a safe distance, held in place by its gravity, circling endlessly, never falling in because the geometry won't permit it, never escaping because you don't have the velocity. It would be a strange kind of orbit, around an object you could see but never approach, an object that broadcasts its presence through gravity and light, but remains fundamentally inaccessible. Another paradox to add to the list of reasons why white holes are among the strangest objects physics has ever imagined. Some theories propose that black holes might transform into white holes when they finish evaporating through Hawking radiation. Black holes aren't eternal. Stephen Hawking showed us this in the 1970s when he demonstrated that quantum effects near the event horizon cause black holes to emit radiation, very slowly losing mass in the process. For a stellar mass black hole, this evaporation would take an incomprehensibly long time, far longer than the current age of the universe, longer than stars will shine, longer than galaxies will maintain their current forms. But eventually, given enough time, a black hole would shrink, its temperature rising as it contracted, until in its final moments it would evaporate in a flash of radiation. But what happens in those final moments? What becomes of the black hole when it's radiated away almost all its mass, when it's shrunk to quantum scales where our usual descriptions of space-time break down? Some physicists, exploring the intersection of quantum mechanics and general relativity, have proposed something remarkable. The black hole might not simply disappear. Instead, it might transform into a white hole, its final act a reversal, matter and energy that fell in long ago suddenly erupting outward. The idea emerges from loop quantum gravity, one of several approaches to understanding how gravity works at quantum scales. In this framework, space-time isn't smooth and continuous at the smallest levels but discrete, made of tiny quantum grains. When a black hole collapses to sizes approaching these quantum scales, the collapse might not continue all the way to a singularity. Instead, quantum effects could cause a bounce, a reversal that turns the black hole inside out, transforming it into a white hole. If this happens, the white hole wouldn't last long, perhaps just long enough to eject whatever matter and information had been trapped inside the black hole, resolving in one dramatic moment the information paradox that's puzzled physicists for decades. The transformation would be violent, energetic, possibly observable as a burst of radiation or particles, and then the white hole would decay, evaporate or transform again, leaving behind only radiation and the ghost of what once was. It's a beautiful idea, though deeply speculative. We have no direct evidence for this transformation, no observation of a black hole's death throes, but it suggests that even endings might contain beginnings, that the universe might be more cyclical than we imagine, matter and energy constantly transforming, nothing truly lost, everything eventually returned in some form to the cosmos that created it. White holes represent a time-reversed region of space-time with an opposite arrow of time. Time is supposed to flow in one direction. You remember yesterday but not tomorrow. Causes precede effects. The future is open, the past is fixed. These seem like fundamental truths about reality, so basic that we rarely question them. But they're not really laws of physics in the way that gravity or electromagnetism are. They're emergent properties, patterns that arise from the underlying dynamics of matter and energy, and in a white hole, these patterns might run backward. Imagine standing at the event horizon of a white hole, if such a thing were possible. From your perspective, watching from outside, you'd see matter emerging from the horizon, streaming outward into space. But here's what's strange. From the perspective of that matter, it didn't emerge from anywhere. It was always there in a sense, existing in a region of space-time where the past extends backward infinitely, where there was no moment of creation, no origin point. The matter's world line, its path through space-time, traces backward from the horizon into a region that's causally disconnected from our universe. This is what physicists mean when they say the arrow of time is reversed in a white hole. It's not that clocks run backward or that effects precede causes in some simple sense. It's that the entire causal structure is inverted. What we experience as future-directed, matter-moving, entropy increasing causes leading to effects, all of this appears reversed from the white hole's perspective. The singularity that, in a black hole, lies in the future, lies instead in the past for a white hole. The horizon that traps matter in a black hole's future releases matter from a white hole's past. Of course, this description strains language to its breaking point. We don't have good words for regions of space-time where causality works differently than we're used to. We try to describe them using temporal language: past, future, before, after. But these words carry assumptions about time's arrow that don't apply in these exotic geometries. It's a bit like trying to describe colour to someone who's never seen, or music to someone who's never heard. The concepts slip through the net of everyday language. Maybe that's appropriate. White holes exist at the boundary of what can be meaningfully discussed, objects that challenge not just our physics but our ability to think and communicate about physics. They remind us that the universe might contain structures so foreign to our experience that understanding them requires not just new theories, but new ways of thinking entirely. The mathematics of white holes is identical to black holes, just with time's direction flipped. There's a peculiar elegance to the relationship between black holes and white holes. Take the mathematical description of a black hole, the Schwarzschild metric perhaps, or the more complex Kerr metric for rotating black holes, and perform a simple transformation. Replace time t with negative time minus t. What emerges is the white hole solution, identical in every way except for this reversal. This mathematical operation, time reversal, is so simple that it feels almost trivial. Just flip a sign and you've transformed one exotic object into another, but the implications are profound. It reveals that the laws of general relativity, Einstein's equations describing how matter and energy curve spacetime, are time-symmetric at their core. They don't inherently prefer one direction of time over another. They describe black holes and white holes with equal validity, treating them as dual solutions to the same underlying equations. This symmetry appears throughout physics, actually. Newton's laws of motion are time-symmetric. They work equally well run forward or backward. Maxwell's equations for electromagnetism don't distinguish between past and future. Even quantum mechanics preserves time reversal symmetry at a fundamental level, though this gets complicated when you include certain weak force interactions. The basic dynamical laws of physics, the equations describing how systems evolve, generally don't care which direction time flows, and yet the universe clearly does care. We age forward, not backward. Heat flows from hot to cold, never spontaneously reversing. Black holes form from collapsing stars, but white holes apparently don't form from anything. Somewhere between the time-symmetric fundamental laws and the time-asymmetric universe we observe, something breaks the symmetry. Something chooses a direction. Physicists call this the arrow of time problem, and it's one of the deepest mysteries in physics. Why does time have a direction? Why do we remember the past but not the future? Why does entropy increase? The fact that our fundamental equations allow both black holes and white holes, but nature implements only one, is a clue. It suggests that the arrow of time isn't written into the basic laws, but emerges from something else, initial conditions perhaps, or the expansion of the universe, or some principle we haven't discovered yet. White holes, in their absence, teach us as much as black holes do in their presence. No stable white hole has ever been found in computer simulations of the universe's evolution. Physics in the modern age often happens inside computers. When dealing with systems too complex for analytical solutions, and general relativity near black holes is definitely too complex, physicists turn to numerical simulations. They discretize space-time into a grid, encode Einstein's equations into algorithms, set up initial conditions, and let the computer evolve the system forward, step by step, watching what emerges. These simulations have been extraordinarily successful. They've predicted the gravitational wave signatures of merging black holes, later confirmed by LIGO's detectors. They've modelled the formation of galaxies, the behaviour of accretion disks, the dynamics of space-time around rotating black holes. They've explored cosmic inflation, structure formation, the evolution of the early universe. And in all these simulations, across all these scenarios, stable white holes have never appeared. Researchers have tried, of course. You can set up initial conditions that approximate a white hole, create the right geometry, impose the right matter distribution. But when you let the simulation run, something always goes wrong. The white hole doesn't persist. It either collapses into a black hole, dissipates into radiation, or transforms into something else entirely. The instabilities that the mathematics predicts manifest vividly in the simulations. Perturbations grow, horizons deform, the carefully constructed geometry unravels. This computational evidence strengthens the case that white holes, while mathematically valid, are physically unrealizable. If there were any natural process that created stable white holes, we'd expect to see them emerge in simulations of cosmic evolution, just as black holes emerge naturally from simulated stellar collapse. The fact that they don't suggests that the universe's initial conditions, its laws of thermodynamics, its quantum properties, all conspire to prevent white holes from forming or persisting. Of course, simulations have limitations. They discretize what should be continuous, approximate what should be exact, impose numerical schemes that might introduce artifacts. But the consistency of the results across different simulation techniques, different resolutions, different approaches to handling Einstein's equations, makes a compelling case. The computers, like nature itself, seem to reject white holes, finding them unstable, unsustainable, incompatible with the universe as it actually evolves. Some physicists think fast radio bursts, mysterious cosmic signals, might be signs of white holes. Every few minutes, somewhere in the observable universe, a telescope detects a fast radio burst. A brief, intense pulse of radio waves lasting just milliseconds, but carrying as much energy as the sun emits over several days. These bursts come from cosmological distances, billions of light years away, and most of them have never repeated. They appear once, brightly, then nothing. We've collected hundreds of them now, maybe thousands, and we still don't fully understand what causes them. We have some good explanations for many of them. Magnetars, neutron stars with incredibly strong magnetic fields, can produce flares that match the observed properties. Some bursts seem associated with distant galaxies, suggesting stellar events of some kind, but others remain mysterious, appearing in regions of space with no obvious source, no galaxy, no star, nothing that should produce such intense radio emission. Could some of these be white holes? The idea is speculative, but not absurd. If a white hole formed briefly, perhaps from quantum fluctuations, perhaps as the death throes of a black hole, it would eject matter and energy in a violent burst. This outflow would include radio waves, among other wavelengths, and the brief duration of the white hole's existence would match the brief duration of the radio burst. Then the white hole would decay, leaving nothing behind to observe in follow-up studies, which matches what we see, a flash, then silence. The timing works too. White holes, being unstable, wouldn't last long. Estimates suggest they might exist for milliseconds to seconds before decaying, which aligns with the duration of fast radio bursts, and the energies involved, though enormous by everyday standards, are plausible for an object ejecting matter from an event horizon. Of course, this explanation faces the same problem all white hole hypotheses face. We've never confirmed white holes exist. Invoking them to explain fast radio bursts is a bit like explaining one mystery with another mystery. Most astronomers prefer more conventional explanations, magnetars, merging neutron stars, other energetic but understood phenomena. But the universe is vast and strange, and maybe some of these signals, the ones that don't fit our models, are hints of something more exotic, something that exists only briefly before vanishing, leaving behind just a whisper of radio waves to mark its passage through our cosmos. A white hole would have a singularity at its centre, just like a black hole, but you could never reach it. Singularities are places where mathematics breaks down, where the equations of general relativity produce infinities, where curvature becomes infinite and space-time itself seems to tear. In a black hole, the singularity lies at the centre, hidden behind the event horizon, and everything that falls in eventually reaches it. Time and space switch roles inside the horizon, and the singularity becomes not a place but a moment, a point in your future that you cannot avoid, no matter which direction you accelerate, no matter what you do. A white hole has a singularity too, mathematically identical to the black holes, but positioned differently in the structure of space-time. Instead of lying in your future, unavoidable and inevitable, it lies in your past. It's a boundary not of endings, but of beginnings, a moment from which the white hole's matter emerged rather than toward which it falls. And crucially, fatally, you cannot reach it. Not because you lack the technology or the courage, but because reaching it would require travelling backward through time, violating causality in ways the universe doesn't permit. Think about what this means. The singularity is there, at the centre of the white hole, a point of infinite density and curvature, just like in a black hole. But whereas the black hole's singularity is in the causal future of anything inside the horizon, meaning it will inevitably affect you, you will inevitably reach it, the white hole's singularity is in the causal past. It has already happened, already finished whatever role it played. You can see its effects, the matter streaming outward from the horizon, but you cannot touch it, cannot probe it, cannot investigate it directly. This creates a profound asymmetry in what we can know. Black holes, for all their mystery, can be studied by things falling into them. We can send probes, watch matter spiral inward, observe what happens at the horizon. But white holes offer no such access. The singularity that birthed them is forever out of reach, separated not by distance but by the one-way flow of time. It's knowledge that exists but cannot be obtained, a truth forever sealed behind the barrier of causality. Perhaps this is fitting. Singularities represent the limits of our theories, the places where general relativity admits it cannot describe what's happening. Maybe it's appropriate that at least one type of singularity remains not just practically, but fundamentally unknowable, a reminder that some questions cannot be answered, some mysteries cannot be solved, no matter how far our understanding extends. The concept challenges our understanding of causality. How can something eject matter without a prior cause? We're deeply accustomed to causality. Every effect has a cause. The ball moves because you kicked it. The water boils because you heated it. Events don't simply happen, they're brought about by prior events, which were themselves brought about by still earlier events, chains of causation extending backward through time. It's so fundamental to how we understand the world that we rarely question it. But white holes force us to question it. Imagine watching a white hole eject matter. You see particles streaming outward from the horizon, carrying energy, possessing momentum, moving through space. Naturally, you ask, why? What caused this ejection? Where did this matter come from? And the mathematics offers an answer that feels deeply unsatisfying. It came from the singularity in the past. But that singularity isn't an event that happened at some specific time. It's a boundary condition, a feature of the space-time geometry itself. The matter wasn't created, it didn't originate anywhere. It simply is, emerging from a past that extends infinitely backward, causally disconnected from anything we could point to and call a cause. This violates our intuitive sense of how things work. Effects should have causes. Emergence should have origins. But white holes seem to create effects without causes, or at least without causes that exist in the same space-time we inhabit. It's as if the white hole reaches backward into a past that never connects to our present, pulling matter from nowhere and ejecting it into our universe. Some physicists suggest this is precisely why white holes can't exist. Causality is too fundamental to violate. The universe has mechanisms we don't fully understand yet that prevent causality violations from occurring or persisting. Maybe quantum effects destroy nascent white holes before they can establish themselves. Maybe the initial conditions of the Big Bang were specifically chosen to exclude white hole formation. Maybe there's a deeper principle, a cosmic censorship of some kind that forbids effects without causes. Or maybe our understanding of causality is incomplete. Maybe what we think of as the one-way chain of cause and effect is actually more flexible, more negotiable at the extremes of curved space-time. Maybe white holes, if they exist, are teaching us that causality isn't a universal law, but an emergent pattern that holds in normal conditions but breaks down in exotic geometries. Perhaps the universe is stranger than our philosophy allows, and white holes are glimpses of that strangeness, hints that reality operates on principles we haven't yet grasped. Some loop quantum gravity theories suggest small white holes might form from quantum fluctuations. At the smallest scales, distances around the Planck length, about 10 to the power of minus 35 meters, far smaller than atoms, smaller than nuclei, smaller than anything we can directly observe, spacetime itself might not be smooth and continuous. Instead, it might be grainy, discrete, made of tiny quantum chunks that fluctuate and bubble like foam on an ocean surface. This is the domain of quantum gravity, where general relativity and quantum mechanics meet, and one of the approaches to understanding this meeting is called loop quantum gravity. In loop quantum gravity, space-time has structure at the Planck scale, a kind of woven fabric made of quantum threads, loops that link and twist to create the geometry we perceive as space and time. And in this quantum foam, fluctuations occur constantly. Virtual geometries appear and disappear, tiny bubbles of curved space-time that exist for the briefest instants before dissipating back into the quantum vacuum. Some researchers working in this framework have suggested that these fluctuations might, occasionally, produce small white holes, miniature versions, existing for incredibly brief moments, far too small and short-lived to observe directly but nonetheless real features of spacetime's quantum nature. These wouldn't be the classical white holes described by Einstein's equations, but quantum objects existing in superpositions, governed by probabilities rather than certainties. If such quantum white holes exist, they'd be utterly different from macroscopic objects. They wouldn't have well-defined horizons or singularities in the classical sense. They'd exist in quantum superposition, neither definitely here nor there, neither definitely present nor absent, and they'd decay almost instantly, existing for perhaps 10 to the power of minus 43 seconds, the Planck time, before transforming back into the quantum foam from which they emerged. Would we call these white holes in any meaningful sense? Maybe, maybe not. They'd bear the same relationship to classical white holes that virtual particles bear to real particles, similar in some respects, profoundly different in others, existing in a regime where our usual concepts of object and existence become fuzzy and uncertain. But if they're real, even in this quantum sense, they'd represent the only white holes nature actually produces, not cosmic-scale fountains of matter, but microscopic quantum fluctuations, occurring constantly at scales far below anything we can observe, part of the fundamental texture of spacetime itself. If white holes existed at the Big Bang, they would have contributed to the universe's initial expansion. The first moments after the Big Bang were chaotic beyond imagining. In the first fraction of a second, the universe expanded exponentially during cosmic inflation, spacetime itself stretching faster than light. Quantum fluctuations got amplified to cosmic scales. Matter and antimatter annihilated in vast quantities. The fundamental forces separated from their unified state. It was a time of extremes, when conditions existed that will never be replicated in the universe's future, when the laws of physics operated in regimes we can barely model. If white holes were ever going to exist naturally, that would have been the time. Some cosmologists have speculated that white holes might have formed in the earliest moments, perhaps as quantum fluctuations in the incredibly dense hot primordial universe, perhaps as relics of whatever process initiated the Big Bang itself. And if they existed, they would have contributed to the expansion, their ejection of matter and energy adding to the outward rush of space-time. Think about what the early universe was, a state of incredibly high density expanding rapidly. Now imagine white holes scattered through this expanding space, each one ejecting matter and energy outward. They would have accelerated the expansion, contributed to the distribution of matter, perhaps influenced which regions became denser and which became voids. In a sense, they would have been cosmic seeds, points from which matter streamed outward, helping to shape the large-scale structure that eventually became galaxies, clusters, the cosmic web. Of course, if such white holes existed, they didn't survive. By the time the universe cooled enough for stable atoms to form, by the time the cosmic microwave background was released, any primordial white holes would have long since decayed or transformed. We see no evidence of them in the CMB's temperature fluctuations, no signature in the distribution of matter, no hint in the abundance of elements forged in those first minutes, but maybe their influence is hidden in plain sight, woven into the initial conditions we observe but don't fully explain. Maybe some of the universe's large-scale features, the pattern of density fluctuations, the specific distribution of matter and energy, carry subtle signatures of white holes that existed briefly at the dawn of time, their effects persistent even though they themselves have vanished. It's speculation, but it's the kind of speculation that reminds us how much we still don't understand about where the universe came from and why it looks the way it does. The absence of white holes in our universe suggests time has a preferred direction at cosmic scales. Here's something remarkable about the laws of physics. Most of them don't care which direction time flows. Write down Newton's laws, Maxwell's equations, even the Schrödinger equation of quantum mechanics, and you'll find they work equally well whether time runs forward or backward. Film a planet orbiting a star, then play the film in reverse, and it still obeys Newton's laws. The fundamental dynamics are time-symmetric, and yet, the universe is not time-symmetric. Ice melts. It doesn't unfold. Organisms age. They don't grow younger. Stars burn fuel and fade. They don't gather scattered light and unfuse helium back into hydrogen. Everywhere we look, we see processes that work in only one direction. A cosmic arrow of time pointing from past to future, from order to disorder, from low entropy to high entropy. The absence of white holes is a particularly striking example of this asymmetry. If the fundamental equations of general relativity are time-symmetric, and they are, then black holes and white holes should be equally permissible. Nature should create both, or neither. But instead, nature creates black holes readily, from stellar collapse from galactic centers, perhaps from the early universe, and it creates no white holes at all as far as we can tell. This suggests that something beyond the fundamental equations determines what actually exists. Perhaps it's the initial conditions of the Big Bang, which started the universe in a state of unusually low entropy, setting up the gradient that entropy increases along. Perhaps it's the expansion of the universe itself, which creates an arrow of time cosmologically. Perhaps it's something about quantum mechanics and measurement that breaks time reversal symmetry in subtle ways. Whatever the explanation, the absence of white holes teaches us that time's arrow is real, fundamental, written into the universe at a level deeper than the dynamical equations. The cosmos doesn't just appear to age in one direction, it actually does, and mechanisms exist, mechanisms we don't fully understand, that enforce this directionality, that permit black holes while forbidding white holes, that allow entropy to increase while preventing it from decreasing. It's a profound asymmetry, one of the deepest features of our universe, and white holes, in their conspicuous absence, help reveal it. Sometimes what doesn't exist teaches us as much as what does. White holes cannot emit Hawking radiation because they have nothing inside to evaporate. Hawking radiation is one of the most beautiful predictions of theoretical physics. The idea that black holes aren't entirely black, that they emit faint radiation due to quantum effects near the event horizon, slowly losing mass over eons until they eventually evaporate completely. Stephen Hawking showed that the intense curvature near a black hole's horizon creates particle-antiparticle pairs from the quantum vacuum, with one particle falling in while the other escapes, carrying energy away from the black hole. But white holes break this mechanism in a fundamental way. Hawking radiation works because particles can fall into the black hole, crossing the horizon inward, allowing the process to extract energy from the black hole's mass. The black hole has an interior, a reservoir of mass energy that can be gradually depleted. But white holes have no such interior that's accessible from the outside. Their horizon forbids inward crossing. Nothing can fall in, which means the quantum process that generates Hawking radiation cannot operate in the same way. Does this mean white holes would be completely stable, eternal if they somehow formed? Not necessarily. Other quantum effects might still cause them to decay. The instabilities we've discussed, the violations of thermodynamic principles, the general incompatibility between white holes and the way time flows in our universe. But they wouldn't evaporate through Hawking radiation specifically. wouldn't slowly diminish through the quantum leakage that dooms black holes to eventual death. This asymmetry reveals something deep about the relationship between quantum mechanics and gravity. Hawking radiation isn't just a property of curved spacetime, it's a property of horizons that trap things, that separate the knowable from the unknowable in a particular direction. White holes have horizons, but the wrong kind for this quantum process to operate. They can release, but not capture, which breaks the mechanism that would allow them to radiate. Perhaps this is another reason nature rejects white holes. Black holes, for all their strangeness, participate in the universe's thermodynamics. They have entropy, temperature, they emit radiation and eventually return their mass to the cosmos. White holes would stand outside this framework, objects without thermodynamic properties in the usual sense, unable to exchange energy with their surroundings in the ways other objects do. And maybe the universe requires thermodynamic participation as a condition for existence. Maybe objects that can't play by thermodynamic rules simply aren't permitted to persist, regardless of what the equations might allow. Some scientists propose that white holes might exist in other universes within a multiverse. Our universe might not be alone. Various theories in cosmology and quantum mechanics suggest the possibility of a multiverse, countless other universes, each with potentially different laws of physics, different fundamental constants, different initial conditions. Some universes might have stronger gravity, others weaker. Some might permit stable atoms, others might not. The space of possibilities is vast, perhaps infinite, and our universe represents just one point in this enormous landscape. And in some of those other universes, white holes might exist. Perhaps in a universe where the arrow of time works differently, where entropy can decrease as easily as increase, white holes would be as common as black holes are here. Perhaps in a universe with different quantum properties, the instabilities that destroy white holes in our cosmos wouldn't operate, and white holes could form and persist. Perhaps somewhere in the multiverse there's a universe where white holes fountain matter into space, visible across cosmic distances, studied by beings who find black holes implausible and white holes ordinary. This possibility is deeply speculative, of course. We have no direct evidence for other universes, no way to observe them or test predictions about them. The multiverse exists primarily as a theoretical construct, a way of thinking about the broader implications of our physical theories. But it provides a kind of intellectual comfort when contemplating white holes, the idea that just because they don't exist here doesn't mean they don't exist anywhere. Maybe the conditions that prevent white holes in our universe are specific to our particular set of physical laws and initial conditions. Maybe the Big Bang that birthed our cosmos started with low enough entropy, or expanded in just the right way, or had quantum properties that specifically exclude white hole formation. But other Big Bangs, other cosmic births, might have different properties, and in those other realities white holes might flourish. It's a reminder that what we observe might not exhaust what's possible. Our universe is remarkably well suited for our existence. The constants are right for atoms, for chemistry, for stars and planets and life. But it's probably not the only configuration that permits interesting complexity, and among those other configurations some might include white holes as natural, stable, observable objects. We just happen to live in a universe that chose differently, that selected black holes from the menu of possibilities and left white holes unrealized, at least here, at least now. A white hole's event horizon would expand as it ejects matter, growing larger over time. Black holes grow by consuming. When matter falls across the event horizon, the black hole's mass increases, and so does the radius of its horizon. Feed a black hole a star, and it becomes larger, more massive, its gravitational influence extending farther. This is why supermassive black holes at galactic centers can reach billions of solar masses. They've been feeding for billions of years, growing steadily as material spirals inward. White holes would work in reverse. As matter streams outward from the horizon, the white hole loses mass. You might expect this to make the horizon shrink, the way a balloon deflates as air escapes. But the geometry works differently. In the mathematics of white holes, the event horizon actually expands as matter is ejected, growing larger as the white hole loses mass. It's counterintuitive, one more way these objects defy everyday expectations. The reason has to do with how horizons are defined in general relativity. They're not physical surfaces but geometric boundaries in spacetime defined by light's behavior. The horizon marks the region from which light rays can escape to infinity versus the region from which they cannot, or in a white hole's case, the region into which light rays cannot enter. As matter streams outward, carrying energy and momentum, it affects the spacetime geometry around the white hole, and this geometric change manifests as an expanding horizon. Imagine watching a white hole over time. Again, if such observation were possible. You'd see matter erupting continuously from a boundary, and that boundary would grow, spreading outward like an expanding sphere, even though the object is losing mass rather than gaining it. It's the opposite of watching a black hole evaporate through Hawking radiation, where the horizon shrinks as the black hole loses mass. Same physical quantity, mass, changing in the same direction, decreasing, but opposite effects on the horizon's size. This expansion creates another problem for white hole stability. An expanding horizon means changing geometry, and changing geometry means the white hole isn't in equilibrium. It's a dynamic object, evolving, and evolution tends to introduce instabilities. The larger the horizon grows, the more surface area exists for quantum fluctuations to affect it, the more opportunities for perturbations to destabilize the entire structure. It's yet another mechanism by which nature might destroy white holes, ensuring they remain theoretical curiosities rather than astrophysical realities. The interior of a white hole might contain an entire universe's worth of information. Information is physical. This is one of the profound insights from 20th century physics, the realization that information isn't just an abstract concept, but a real property of physical systems, something that can be quantified, stored, transformed, and conserved. The exact state of every particle, every field, every degree of freedom in a system constitutes information, and various principles suggest this information cannot be destroyed, only scrambled or transformed. A white hole's interior would be a sealed vault of information, causally disconnected from the outside universe, but nonetheless containing, potentially, vast amounts of data. Everything about the white hole's state, its history, whatever processes created it, all of this would be encoded in the geometry and matter distribution of the interior region, but we could never access it. The causal structure prevents any signal from travelling from the interior to the exterior, any information from crossing that boundary in the inward direction. Think about what this means. There could be an entire universe's worth of complexity hidden inside a white hole. Detailed structure, intricate patterns, information equivalent to the entire history of a cosmos, and it would be fundamentally unknowable to us. We could observe the white hole's exterior properties, its mass, perhaps its charge or angular momentum if it's rotating or electrically charged, but the interior, sealed away, forever separated by the geometry of spacetime itself. This creates an interesting tension with the holographic principle, an idea in theoretical physics suggesting that all the information in a region of space can be encoded on its boundary. If the holographic principle is correct, then maybe the white hole's interior information isn't truly inaccessible. Maybe it's somehow encoded on the horizon, available in principle even if practically impossible to decode. Or maybe white holes represent a case where the holographic principle doesn't apply, a region of space-time that genuinely keeps secrets. Either way, it's a humbling thought. The idea that information could exist, concrete, definite information about real physical states, and be permanently beyond our reach, not because it's far away or hard to measure, but because the universe's causal structure has drawn a boundary we cannot cross. Some knowledge, it seems, might be forever out of bounds, locked away in regions of space-time we can see but never touch, know exist but never understand. White holes raise profound questions about whether the laws of physics are truly time-symmetric. Symmetry is beautiful to physicists. When a law of physics remains unchanged under some transformation, flipping left and right, or rotating coordinates, or reversing time, it suggests something deep and fundamental. Symmetries often point toward conservation laws, toward underlying principles more basic than the laws themselves. Time reversal symmetry in particular seems fundamental to most of physics. Run the equations backward, and they still work. But white holes challenge this symmetry in a profound way. Yes, the equations of general relativity permit both black holes and white holes with perfect mathematical democracy. But the universe doesn't exhibit this democracy. It creates one but not the other. choosing a preferred direction despite the equation's indifference. This suggests that time reversal symmetry, while present in the fundamental equations, is broken at the level of what actually exists. Physicists distinguish between laws being symmetric and solutions being symmetric. The laws of physics might be time reversible, but the specific configuration of matter and energy in our universe, the initial conditions, the boundary conditions, the particular solution to the equations that describes our cosmos, need not be. It's like how the laws of architecture are symmetric with respect to rotation, but actual buildings aren't symmetric. They face particular directions, have specific orientations, break the symmetry that the general principles allow. So maybe white holes are teaching us that we need to distinguish more carefully between what the laws permit and what the universe implements. The laws of physics describe possibility space, the full range of what could exist. But something else, call it initial conditions, call it the arrow of time, call it thermodynamic constraints, selects from this possibility space, choosing which solutions to realize and which to leave as mathematical abstractions. This raises deep questions. Why these initial conditions and not others? Why does time have an arrow? Why does the universe age in one direction? These questions go beyond the laws of physics as usually formulated, touching on cosmology, thermodynamics, perhaps even questions about why there's something rather than nothing. White holes, in their absence, point toward these deeper mysteries. Remind us that understanding the laws isn't the same as understanding why the universe chose to play by them in this particular way, rather than some other. Some researchers link white holes to the cosmological arrow of time, why the universe ages in one direction. Time flows forward. This seems obvious, trivial even, until you start asking why. Why do we remember yesterday but not tomorrow? Why does a movie played backward look absurd? People walking in reverse, water flowing upward, broken glass reassembling itself. The laws of physics, as we've discussed, mostly don't distinguish between forward and backward. So where does this arrow come from, this fundamental directionality to time that pervades every aspect of our experience? One answer involves entropy, and the second law of thermodynamics, disorder increases as time moves forward. But this just pushes the question back a step. Why did the universe start in a low entropy state, ordered and organized, allowing entropy to increase over billions of years? The Big Bang was extraordinarily smooth, extraordinarily uniform, a state of low entropy that seemed specially chosen. If the universe had started in a random high entropy state, there would be no arrow of time, no preferred direction, no way to distinguish past from future. Some physicists have suggested that white holes, or rather their absence, might be connected to this arrow. If white holes existed in significant numbers, they would represent pockets of decreasing entropy, regions where disorder transforms into order, where the second law runs backward. Their presence would complicate or destroy the universe's overall arrow of time. Perhaps the universe's initial conditions were specifically such that white holes couldn't form, ensuring a consistent arrow of time from the Big Bang forward. Think about it this way. The universe started in a special state, low in entropy, and has been running downhill thermodynamically ever since. Black holes are consistent with this downhill slide. They increase the universe's total entropy by crushing matter into disordered states beyond our ability to measure. White holes would run uphill, decreasing entropy, creating order spontaneously. Their absence might not be coincidental but necessary, a requirement for the universe to have a consistent arrow of time. This connects to deep questions in cosmology. Why was the Big Bang so special? Why did it start with such low entropy instead of the high entropy we'd expect from a random initial state? Maybe the answer involves constraining what kinds of structures can exist, forbidding white holes and other entropy-decreasing phenomena, ensuring time flows consistently in one direction everywhere. It's speculation, but it suggests that understanding white holes, understanding why they don't exist, might be key to understanding one of the most fundamental features of our universe, why it has a past and a future that are qualitatively different, why we age, why change happens, why time matters at all. A white hole cannot be destroyed or merged with other objects according to classical theory. Black holes can merge. We've observed this directly through gravitational waves, two black holes spiraling together, their horizons touching and coalescing into a single, larger black hole, the merger releasing tremendous energy and ripples through space-time. Black holes can also grow by accreting matter, pulling in gas and dust and stars, adding to their mass steadily over time. They're dynamic objects that interact with their environment, change and evolve. But white holes, according to the classical theory of general relativity, cannot be destroyed or merged in any straightforward way. You cannot throw matter into a white hole to make it grow. The horizon forbids entry. You cannot collide two white holes and expect them to merge. The geometry that prevents inward motion also prevents the close approach necessary for merger. They would repel, their horizons pushing against each other in ways that black holes' horizons don't. This invulnerability is both fascinating and problematic. Fascinating because it suggests white holes, if they existed, would be eternal, unchangeable, permanent fixtures of space-time. Once formed, however they formed, they would persist indefinitely, unable to be dismantled or destroyed by any ordinary process. Problematic because it makes them even more incompatible with the dynamic evolving universe we observe. Objects that can't change, can't interact, can't merge or grow or shrink through normal processes seem out of place in a cosmos where everything else evolves. Of course, this invulnerability is only according to classical general relativity. Quantum effects might still destroy white holes, as we've discussed. The instabilities inherent in their structure might cause them to decay or transform. The violation of thermodynamic principles might mean the universe finds ways to eliminate them that aren't captured in the classical equations. But classically, once you have a white hole, you're stuck with it. An eternal, unchanging object that interacts with nothing, affects nothing, persists regardless of what happens around it. It's another mark against their existence, in a way. The universe seems to favour dynamic objects, things that change and evolve and interact. Stars burn and die, galaxies merge. Even black holes evaporate eventually through Hawking radiation. But white holes would be static islands in a flowing river, unchanging points in an evolving cosmos. Nature seems to have no use for such objects, preferring instead the rich dynamics of interaction and change. Perhaps that's why we see none. The universe simply doesn't tolerate eternal, isolated, unchanging structures at cosmic scales. Everything must participate in the grand evolution, and white holes, unable to participate, are excluded from existence. The study of white holes has helped physicists understand the nature of event horizons in general. Sometimes studying what doesn't exist teaches you about what does. White holes, for all their absence from reality, have been valuable thought experiments, tools for understanding the deeper principles of general relativity. By examining how white holes differ from black holes, physicists have learned what's essential about event horizons and what's merely contingent, what follows necessarily from the mathematics and what depends on additional physical constraints. For instance, studying white holes helped clarify that event horizons aren't about forces or barriers in the conventional sense. They're about causal structure, about which regions of spacetime can communicate with which other regions. A black hole's horizon prevents outward communication. A white hole's prevents inward communication. This distinction helped physicists understand that horizons are fundamentally about information flow, about what can affect what, rather than about physical surfaces or walls. White holes also help develop the mathematics of null surfaces, geometric constructions in space-time that are crucial for understanding horizons, gravitational waves, and other relativistic phenomena. Working out the properties of white hole horizons, even though white holes don't exist, led to techniques and insights that proved useful for modelling black holes, analysing their stability, understanding how they interact with infalling matter. And the puzzles white holes present, why don't they exist despite being mathematical valid, have pushed physicists to think more carefully about what distinguishes the physical from the merely mathematical. Not every solution to Einstein's equations corresponds to something real. Understanding which solutions nature implements and which it doesn't requires going beyond the equations themselves, considering thermodynamics, quantum mechanics, causality, initial conditions. White holes have been a case study in this distinction, a clear example of mathematics predicting something nature rejects. In this way, white holes have served as pedagogical tools, helping students and researchers develop intuition about general relativity. They're simpler than many real astrophysical situations, cleaner, easier to analyse, and yet strange enough to force careful thinking about fundamental concepts. They're the theoretical physics equivalent of thought experiments in philosophy, impossible scenarios that nonetheless illuminate real principles. We may never observe a white hole, but the exercise of understanding why we don't has deepened our understanding of spacetime, horizons, and the relationship between mathematics and reality. Some quantum gravity theories suggest microscopic white holes might exist for incredibly brief moments. At the smallest scales, reality becomes uncertain, probabilistic, fuzzy in ways that defy our everyday intuitions. Quantum mechanics tells us that particles can be in multiple places at once, that empty space seethes with virtual particles popping in and out of existence, that measurement changes what's being measured in fundamental ways, and when you combine quantum mechanics with gravity, quantum gravity, space-time itself becomes subject to these quantum uncertainties. In this quantum foam, as it's sometimes called, the geometry of space-time fluctuates wildly at the Planck scale. Virtual black holes might appear and disappear, tiny wormholes might form and collapse, and perhaps, just perhaps, microscopic white holes might flicker into existence for the briefest instants before quantum effects destroy them. These wouldn't be the classical white holes of general relativity, but quantum entities existing in superpositions, governed by probability rather than certainty. The timescales involved are almost incomprehensibly short. The Planck time, about 10 to the power of minus 43 seconds, represents the smallest meaningful unit of time according to current physics. If microscopic white holes exist in quantum foam, they'd persist for roughly this duration or less, appearing and vanishing so quickly that no measurement could ever detect them directly. They'd be part of the quantum background, the fundamental fuzziness that underlies all of reality. Do such objects really exist? We don't know. We don't yet have a complete theory of quantum gravity that would let us calculate definitively. String theory, loop quantum gravity, and other approaches make different predictions about what happens at the Planck scale, and none have been experimentally confirmed. It's possible that quantum white holes are real features of spacetime's microstructure. It's equally possible that they're artifacts of incomplete theories, mathematical possibilities that a final theory of quantum gravity will exclude. But if they exist, they'd be the only white holes nature produces, not cosmic objects observable through telescopes, but quantum fluctuations occurring everywhere, always, at scales far below anything we can measure. In a sense, spacetime itself might be continuously creating and destroying white holes as part of its fundamental structure, the quantum equivalent of waves on an ocean surface. We'd be swimming in white holes without ever noticing, surrounded by them the way we're surrounded by air, their effects visible only in aggregate, in the quantum properties of fields and particles. It's a beautiful thought, in a way, that white holes might exist after all, just not in the form we imagined, not as cosmic fountains, but as quantum sparkles in the fabric of reality itself. White holes would be perfect laboratories for testing our understanding of time reversal symmetry. If we ever found a white hole, if one somehow existed despite all the reasons we've discussed for why they shouldn't, it would instantly become the most important object in physics. Not because of what it would do, but because of what it would teach us. A white hole would be a natural laboratory for testing some of the deepest principles of physics, a place where our theoretical understanding meets reality in unprecedented ways. Time reversal symmetry in particular could be tested directly. Most physics equations work the same forward and backward through time, but we've never had a macroscopic object that actually demonstrates this symmetry. White holes would be that object, the time-reversed version of black holes, exhibiting in observable form what's usually just a mathematical operation in our equations. By studying how white holes behave, how they interact with matter and light, how they evolve over time, we could test whether nature really respects time reversal symmetry, or whether the symmetry is somehow broken at macroscopic scales. We could also investigate causality in ways currently impossible. White holes challenge our understanding of cause and effect by apparently producing effects without causes. Observing one would let us study this violation directly, measure how matter emerges from the horizon, probe whether there's any pattern or predictability to what's ejected. We might discover new principles governing causality, new constraints we hadn't anticipated, or we might find that causality is more flexible than we thought, allowing certain kinds of causal processes under specific conditions. The thermodynamics would be equally fascinating. Does a white hole have temperature? How do you define entropy for an object that seems to violate the second law? Would quantum fluctuations near the horizon produce any observable effects? All of these questions would become empirical rather than theoretical, testable through observation rather than solvable only through mathematics. Of course, this is all academic, we don't have white holes to study. But the fact that they would be such valuable laboratories makes their absence even more tantalizing. It suggests that nature has hidden from us, perhaps necessarily, perhaps contingently, an entire class of phenomena that would revolutionize our understanding of physics. We're left studying black holes and imagining their time-reversed counterparts, learning what we can from the half of spacetime geometry that actually exists while the other half remains forever theoretical. The connection between black and white holes through wormholes remains purely speculative. There's something deeply appealing about the idea that everything falling into a black hole might re-emerge somewhere else, that the universe doesn't destroy information but redirects it, that what appears to be an ending might actually be a doorway. The mathematics of general relativity permits this, in a limited sense. The Einstein-Rosen bridge, connecting a black hole to a white hole through a tunnel in spacetime. But mathematical permission and physical reality are very different things. The wormhole connecting a black hole to a white hole exists in the mathematical solution for only an instant. It's born and collapses faster than light could traverse it, pinching off before any matter or signal could make the journey. You'd need to move infinitely fast to cross before the throat closes, and infinite speed violates the fundamental speed limit of the universe. So even though the connection exists on paper, it's useless as an actual passageway. The door exists but slams shut before you can walk through. Some theoretical work has explored whether exotic matter with negative energy density, could hold the wormhole open, propping up the throat like scaffolding supporting a tunnel during construction. Quantum mechanics permits negative energy in certain configurations, though we've never observed or created it in bulk quantities. If you could gather enough exotic matter and arrange it just right, maybe you could stabilize the wormhole, make it traversable. But this ventures deep into speculation, combining multiple unproven ideas: wormholes, exotic matter, precise control of spacetime geometry, into scenarios that are mathematically interesting but physically dubious. And even if you could stabilize the wormhole, questions remain. Would matter survive the journey? The tidal forces near a black hole's singularity would tear apart anything approaching, spaghettifying it long before it reached any hypothetical wormhole throat. Would information be preserved? How would causality work if you could send signals or matter through spacetime shortcuts? The deeper you examine the scenario, the more problems emerge, each requiring additional speculative solutions. Perhaps that's fitting. The idea of wormholes connecting black holes to white holes is so elegant, so narratively satisfying, that it almost demands to be true. The universe is an interconnected network, nothing truly lost, everything recycled through hidden passages in spacetime. But elegance doesn't guarantee truth, and narrative satisfaction doesn't make physics. The connection remains a beautiful mathematical possibility, a thought experiment that helps us understand spacetime geometry, but almost certainly not a description of how the universe actually works. Some doors, it seems, are meant to remain closed, some connections too unstable to sustain, some shortcuts through reality too good to be true. Some cosmologists propose that dark matter might somehow involve white holes. Dark matter is one of the great mysteries of modern cosmology. We know it's there, or at least we know something is there, because galaxies rotate too fast, galaxy clusters hold together too strongly. Gravitational lensing reveals invisible mass-bending light from distant sources. Whatever dark matter is, it outweighs ordinary matter by about 5 to 1, comprises most of the matter in the universe, and yet doesn't emit, absorb, or reflect light in any wavelength we've observed. It's invisible, detectable only through its gravitational effects. What could dark matter be? The leading candidates are exotic particles, WIMPs, axions, sterile neutrinos, particles predicted by extensions of the standard model of particle physics, but not yet detected despite decades of searching. But occasionally, physicists explore more exotic possibilities. Could dark matter involve black holes? Primordial black holes, perhaps, formed in the early universe, or something even stranger, white holes. The idea faces immediate problems. White holes, as we've discussed, would be bright, constantly ejecting matter and radiation. That's the opposite of dark matter's defining characteristic, being dark, invisible, interacting only gravitationally. How could white holes possibly constitute dark matter when they'd be the most luminous objects imaginable? Some speculative proposals suggest quantum white holes, existing at microscopic scales, might behave differently from classical white holes. Perhaps they interact with matter in unusual ways, gravitating normally but not emitting detectable radiation. Or perhaps white holes from the early universe could have decayed into some stable remnant. Not quite white holes anymore, but objects retaining some white hole properties, including significant mass and minimal interaction with light. These ideas remain on the far fringes of cosmology, mentioned more as logical possibilities than serious proposals. The evidence for dark matter is strong, but all the evidence is gravitational. We infer its presence from how galaxies move, how light bends, how large-scale structure forms. We don't actually know what dark matter is made of, so physicists occasionally entertain exotic possibilities, just in case the answer turns out to be something unexpected, something that current particle physics hasn't predicted. Most likely dark matter is exactly what it seems, some unknown particle, perhaps several types of particles, that interact weakly with ordinary matter and light but strongly with gravity. But the universe has surprised us before, revealing phenomena we hadn't imagined. Maybe somewhere in the space of possibilities, white holes or their remnants play some role in dark matter. Or maybe this is just physicists being thorough, exploring every logical possibility before settling on the answer. Either way, it's a reminder that we still have much to learn about what fills the cosmos, what composes most of its mass, what shapes its evolution on the larger scales. A white hole's gravitational lensing would look identical to a black hole's from a distance. Gravitational lensing is one of the most beautiful confirmations of general relativity, the observation that massive objects bend light, curving the paths of photons passing nearby, just as they curve the paths of material objects. This bending creates lensing effects, multiple images of distant objects, Einstein rings, distortions and magnifications that reveal invisible mass. Black holes create particularly strong lensing. Their intense gravity bends light dramatically, creating characteristic patterns around them. If you looked at a black hole with a bright background, say, with an accretion disk glowing around it, you'd see the disk's light bent in complex ways, creating the shadow we've now photographed, surrounded by a ring of light from photons that barely escaped the gravitational pull. A white hole would create identical lensing patterns. From far away, light doesn't know whether it's being bent by a black hole or a white hole. It only responds to the curvature of spacetime, and that curvature, at a distance, is the same for both objects. The mass, the gravitational field, the way spacetime curves around the horizon, all identical, just with different causal structure that becomes apparent only when you approach closely or watch what crosses the horizon. This means we couldn't identify white holes through gravitational lensing alone. If white holes existed scattered throughout the universe, they'd blend in with black holes gravitationally. We'd need to observe them in other ways, watching for the constant outflow of matter and radiation, looking for the brightness that should accompany their eruptions, noticing that nothing ever falls in while things constantly emerge. The lensing would be identical, but the other properties would distinguish them clearly. Of course, we don't see any objects that match white holes' expected behaviour. Constant bright emission, matter streaming outward, nothing falling in. All the objects we've identified as black holes behave like black holes should. They accrete matter, they grow, they're surrounded by material spiralling inward. The gravitational lensing is consistent with black holes, and so is everything else we observe. The lensing alone wouldn't rule out white holes, but the absence of other expected signatures does. It's an interesting thought experiment, though. Imagine discovering a gravitational lens and having to determine whether it's a black hole or a white hole. You'd measure the mass through lensing, observe the light carefully for signs of outward flows, watch for accretion or emission. The detective work would be fascinating, distinguishing between two objects that are gravitational twins but causal opposites. We just don't seem to live in a universe where that detective work is necessary. All the massive compact objects we find behave as black holes, and none show even a hint of white hole characteristics. The concept helps physicists think about what makes black holes special and why they persist. Sometimes understanding what something is requires understanding what it isn't. Black holes are remarkable objects, regions of space-time so severely curved that they trap light itself, grow by consuming matter, persist for cosmic timescales, and probably constitute some of the most common massive compact objects in the universe. But why? What makes black holes stable when so many other configurations aren't? White holes help answer this by providing a contrast. They're mathematical twins to black holes, identical in geometry but opposite in causal structure. And yet one exists abundantly, while the other apparently doesn't exist at all. By examining this asymmetry, physicists have developed deeper insight into what makes black holes work, what principles ensure their stability, what aspects of the universe's structure favour their formation and persistence. Black holes align with the arrow of time. They form from past events, stellar collapse, and persist into the future, growing through accretion, slowly evaporating through Hawking radiation, participating in the universe's thermodynamic evolution. They increase entropy, accepting matter in ordered states and crushing it beyond recognition, contributing to the universe's march toward disorder. They're thermodynamically favoured, consistent with every principle governing how time flows and entropy increases. White holes would resist all of this. They'd require special initial conditions rather than forming from natural processes. They'd decrease entropy rather than increasing it. They'd eject order rather than consuming it. They'd be fundamentally incompatible with the arrow of time, with thermodynamics, with causality as we experience it. By understanding why white holes don't work, we understand why black holes do. They're not just permitted by the equations, but favoured by nature, compatible with the deep principles that govern cosmic evolution. This kind of understanding, by contrast, by studying what's excluded, is powerful in physics. It's not enough to know that something exists. You want to know why it exists rather than the alternatives. Black holes exist rather than white holes because the universe has an arrow of time, because entropy increases, because causality flows forward, because thermodynamics places constraints beyond what the geometric equations alone require. White holes, in their absence, illuminate these constraints, helping us see the full landscape of what's possible and understand why nature chose the particular path it did. White holes appear in the maximally extended Schwarzschild solution, a complete map of black hole spacetime. When physicists solve Einstein's equations, they often start with simplified cases, objects that aren't rotating, aren't charged, exist in otherwise empty space. The Schwarzschild solution is one of these, the geometry around a non-rotating, uncharged massive object, the simplest possible black hole. But you can extend this solution, following the mathematics to its logical conclusion, creating what's called the maximally extended Schwarzschild solution, a complete map of all the regions that the geometry permits. This map is strange and wonderful. It includes the familiar exterior region, the space around the black hole where we live and observe. It includes the black hole interior, the region inside the event horizon, where all paths lead to the singularity. But it also includes mirror regions, another exterior, causally disconnected from ours, and a white hole interior, a region from which matter can emerge but into which nothing can fall. And connecting these regions are wormholes, Einstein-Rosen bridges, theoretical passageways that exist mathematically, but collapse before anything can traverse them. The maximally extended solution is a theoretical construct, a way of exploring what the mathematics allows without worrying about whether nature implements it. Most physicists believe the white hole regions don't correspond to anything real. They're artifacts of extending the solution beyond the physical situation it describes. After all, real black holes form from stellar collapse, and that process creates only the black hole regions, not the white hole counterparts. But the maximally extended solution remains valuable pedagogically and conceptually. It shows the full scope of what the equations permit, reveals symmetries that aren't obvious in more limited solutions, and demonstrates how general relativity connects different regions of spacetime through geometric structure. It's a map of possibility space, showing all the territories the equations describe whether or not travellers ever visit them. Looking at these diagrams, the Penrose diagrams that represent the maximally extended solution, you see a kind of beauty in the mathematics, a symmetry and completeness that goes beyond what exists. There are regions we can never reach, horizons we can never cross, singularities that exist only in forbidden territories. White holes are scattered through these diagrams, mirror images of black holes, equal partners in the mathematical structure even if nature grants them no physical reality. Sometimes the maps we draw are more complete than the territories they describe, and that completeness itself teaches us something about the relationship between mathematics and physics, between what can be written down and what can exist. Some researchers suggest white holes might explain the universe's matter-antimatter asymmetry. One of the deepest puzzles in cosmology is this: why is there more matter than antimatter in the universe? According to our best theories, the Big Bang should have created matter and antimatter in equal quantities, particles and antiparticles, perfect symmetry, and when matter and antimatter meet, they annihilate, converting entirely to energy. So we'd expect a universe filled mostly with photons, the remnant radiation from near-total annihilation, with perhaps a few stray particles left over. But that's not what we observe. We see galaxies, stars, planets, people, all made of matter, with antimatter appearing only briefly in high-energy collisions or cosmic ray interactions. Something broke the symmetry. Something caused the early universe to produce slightly more matter than antimatter, about one extra matter particle for every billion matter-antimatter pairs. This tiny asymmetry, this slight imbalance, is why anything exists at all. After the annihilation epoch, when most matter and antimatter destroyed each other, this small excess remained, and from it, everything we see was built. What caused this asymmetry? We don't fully know. There are proposals involving particular physics beyond the standard model, processes that favour matter production over antimatter under specific conditions. But some physicists have speculated, very speculatively, that white holes in the early universe might have played a role. If white holes existed briefly after the Big Bang, and if their ejection processes somehow favoured matter over antimatter, they could have seeded the asymmetry that eventually filled the universe with atoms instead of leaving it as a sea of photons. The mechanism would need to be specific and particular. White holes would have to eject matter and antimatter at different rates, or perhaps create conditions where matter survives preferentially over antimatter. The details are unclear and deeply speculative. This is frontier thinking, exploring possibilities more than proposing definite theories. But the connection is intriguing. Two mysteries, both relating to asymmetries, matter-antimatter asymmetry, the asymmetry between black and white holes, both potentially connected to the universe's earliest moments. Most physicists favour other explanations for the matter-antimatter asymmetry, processes involving the weak force, or grand unified theories, or specific mechanisms that don't require white holes at all. The evidence for white holes remains non-existent, so building explanations on them feels like constructing houses on sand. But the universe's early moments were so extreme, so beyond our direct observation, that maintaining some openness to exotic possibilities seems wise. Maybe white holes contributed to why we exist, why the universe is full of matter rather than empty photons. Or maybe the answer lies elsewhere, in physics we understand better or haven't yet discovered. Either way, the question remains, why something rather than nothing? Why matter rather than pure energy? Why a universe capable of complexity rather than simple, eternal equilibrium? The instability of white holes might be connected to the second law of thermodynamics at a deep level. The second law of thermodynamics, that entropy increases in closed systems, isn't just a statistical tendency or an engineering approximation. It's one of the most fundamental principles in physics. Arthur Eddington once called it the supreme law of nature, the one physical principle that would survive even if all our other theories were overthrown. It governs everything from why coffee cools to why the universe evolves, from why engines have limited efficiency to why time seems to flow in one direction. White holes would violate this law, not incidentally but fundamentally as a core aspect of their nature. By ejecting organised matter from their horizons, they'd create order from chaos, decrease entropy spontaneously, run against the universal tide toward disorder. And the universe, it seems, doesn't permit sustained violations of the second law. Individual quantum fluctuations might temporarily decrease entropy in tiny regions for brief moments, but macroscopically, over time, the second law always wins. Perhaps this is the deepest reason for white hole instability. It's not just that they're mathematically unstable in general relativity, or that quantum effects would destroy them, or that they can't form from any known physical process. It's that their very existence would contradict thermodynamics' supreme law, and nature has mechanisms we may not fully understand, that enforce thermodynamic consistency, that prevent or destroy anything attempting to violate entropy's increase. Think about what this means. The second law might not just describe how systems evolve, it might constrain what can exist at all. Objects that would systematically decrease entropy might be forbidden at a fundamental level, excluded from reality by principles deeper than the geometric equations of general relativity. Thermodynamics might trump geometry, constraining which mathematical solutions correspond to physical objects. This suggests a hierarchy in physics. Some principles are more fundamental than others, and when they conflict, the more fundamental principle wins. Einstein's equations permit white holes, but thermodynamics forbids them. And thermodynamics' prohibition appears absolute. It's a reminder that physics isn't just about solving equations, but about understanding which principles take precedence, which constraints are negotiable, and which are inviolable, what the universe permits and what it fundamentally rejects. Maybe someday we'll understand this hierarchy better, see clearly how thermodynamics connects to space-time geometry, understand why entropy increase is so fundamental that it constrains the very structure of reality. White holes, in forcing us to confront this question, serve as test cases, probes into the deep architecture of physical law. Their absence is data, important data, about what kinds of structures the universe allows and what principles govern that allowance. Modern theories suggest that if white holes exist, they would emit matter in quantum superposition states. Quantum mechanics tells us that particles can exist in superposition, multiple states simultaneously, not definitely here or there, but somehow both until measured. An electron can be spin up and spin down simultaneously. A photon can be polarized vertically and horizontally at once. These aren't just gaps in our knowledge, they're genuine features of quantum reality, confirmed by countless experiments central to how the microscopic world operates. If white holes existed and operated under quantum mechanical principles rather than purely classical ones, the matter they eject would likely emerge in quantum superposition states. A particle emerging from a white hole's horizon might not have a definite position, momentum or spin until someone observes it. It would exist in a quantum haze, a superposition of possibilities, fundamentally uncertain and undetermined. This would make white holes even stranger than their classical description suggests. Not only would they eject matter without obvious cause, but that matter would emerge in maximally uncertain states, carrying minimal information about where it came from or what determined its properties. You couldn't predict what a white hole would eject next, not because of practical limitations, but because of fundamental quantum indeterminacy. The universe itself wouldn't know until the moment of emission. This quantum nature might actually be crucial for white holes to exist at all, if they exist. Classical white holes face insurmountable stability problems, but quantum white holes, operating at microscopic scales where quantum effects dominate, might behave differently. The quantum uncertainty might smooth out some of the classical instabilities, or transform them into different phenomena entirely. Perhaps white holes can only exist as quantum objects, not classical ones, making them fundamentally different from black holes, which can exist classically at any scale. Of course, this is deeply speculative. We don't have a complete theory of quantum gravity that would tell us definitively how white holes behave in the quantum regime. Different approaches, string theory, loop quantum gravity, others, make different predictions, and none have been experimentally verified. But the general expectation is that quantum white holes, if they exist, would be thoroughly quantum objects, exhibiting superposition, uncertainty, entanglement, all the strange features that make quantum mechanics so unlike our everyday experience. It's another layer of strangeness to add to white holes' already considerable strangeness. Not just objects that eject rather than attract, not just horizons you can leave but not enter, but sources of quantum uncertainty, fountains of indefinite possibility, objects that blur the boundary between what is and what might be. White holes remain one of the most beautiful purely mathematical objects in physics. There's a certain kind of beauty in mathematical physics that's hard to explain to those who haven't experienced it. The aesthetic pleasure of elegant equations, symmetric solutions, structures that reveal hidden order in apparent chaos. White holes possess this beauty in abundance. even if they don't exist physically. They emerge from the equations of general relativity with the same mathematical grace as black holes, perfect mirror images, solutions that demonstrate time reversal symmetry in its purest form. The mathematics describing white holes is clean, precise, exact. The Schwarzschild solution, extended to include white hole regions, has a geometric perfection to it. Every feature has a counterpart. Every asymmetry in causal structure is matched by an opposite asymmetry elsewhere. The Penrose diagrams displaying white holes have a visual symmetry, a balance that appeals to the pattern-recognizing parts of our minds. It's mathematics doing what mathematics does best, revealing structure, exposing symmetry, showing how complex phenomena emerge from simple principles. And this beauty exists independent of physical reality. White holes are beautiful as mathematical objects whether or not nature implements them. It's like a perfect geometric proof, or an elegant theorem in number theory, or a symphony that explores musical possibilities fully and completely. The beauty is intrinsic to the structure itself, not dependent on correspondence with the physical world. Perhaps this is one reason physicists continue studying white holes despite their apparent non-existence. The intellectual pleasure of working with beautiful mathematics is real, valuable, worth pursuing for its own sake. Understanding white holes deepens understanding of general relativity, even if white holes themselves never appear in telescopes. The mathematics reveals possibilities, explores the full solution space, shows what the theory permits, and what constraints might exclude certain possibilities from reality. There's something profound in this, the idea that mathematics can be beautiful, can be worth studying, can teach us things, even when it describes objects that don't exist. Not every grammatically correct sentence is true, but studying grammar still teaches us about language. Not every mathematical solution corresponds to physical reality, but studying mathematics still teaches us about the structure of our theories, the principles underlying them, the full landscape of what they describe. White holes live in this space, mathematically real, physically absent, beautiful regardless. They're poems in the language of general relativity, perfect constructions that demonstrate what the theory can say, even if nature chooses not to speak those particular words. The mystery of white holes reminds us that mathematics can predict possibilities nature never chooses to realize. We've come full circle, in a way, back to where we started, but with deeper understanding. White holes exist perfectly in mathematics, exact solutions to Einstein's field equations, predicted with the same rigor that predicted black holes, gravitational waves, the bending of starlight, all the confirmed triumphs of general relativity. And yet nature apparently doesn't implement them, doesn't choose this particular possibility from the space of mathematical solutions. This is a profound lesson about the relationship between mathematics and physics. Mathematics is the language we use to describe nature, and it's an extraordinarily effective language. Eugene Wigner once called it unreasonably effective, puzzling over why abstract mathematics should correspond so precisely to physical reality. But mathematics is also broader than physics, describes more than exists, explores logical possibilities whether or not they're physically realized. White holes remind us of this distinction. They're mathematically impeccable. The equations that describe them are as valid as any in physics, the derivations as rigorous, the predictions as definite. But something outside the mathematical equations themselves, thermodynamics perhaps, or the arrow of time or quantum effects or the universe's initial conditions, selects which mathematical possibilities become physical actualities. Not everything that can be written can exist. This humbles us, in a good way. It suggests that physics requires more than solving equations, more than finding mathematical solutions. It requires understanding what principles constrain the solutions, what additional criteria determine which possibilities nature realizes, why some mathematical truths correspond to physical truths, while others remain abstract. The equations cast a wide net. Reality fills only part of it. And yet, studying the full space of solutions, including the unrealized ones, teaches us about the structure of our theories, about what they permit and what they require, about how different principles interact and sometimes conflict. White holes have been valuable thought experiments, testing grounds for ideas, tools for understanding general relativity more deeply. They've taught us about event horizons, causality, time reversal symmetry, thermodynamics, the arrow of time, So perhaps white holes serve their purpose after all, not as physical objects but as conceptual tools, not as things to observe but as ideas to think with. They exist in that strange space between the purely imaginary and the concretely real, more than fiction, less than fact, mathematical truths that illuminate physical principles even without manifesting physically. And maybe that's enough. Maybe the universe doesn't need to realize every possibility for those possibilities to matter, to teach us, to expand our understanding. White holes exist where they've always existed, in the equations, in our minds, in the space of what could be, and from there, they illuminate what is, casting light on the universe we inhabit by showing us the universe we don't. We've drifted through 50 facets of white holes tonight, objects that exist perfectly in mathematics but apparently nowhere in reality, cosmic fountains that would eject rather than attract, horizons you could exit but never enter, singularities in the past instead of the future. We've seen how they emerge from the same equations that describe black holes, how they challenge our understanding of time and causality and thermodynamics, how their absence teaches us as much as their mathematical presence. Perhaps white holes are the universe's way of showing us the boundary between what can be written and what can exist, between logical possibility and physical actuality. They remind us that mathematics is a tool for exploring ideas, and nature is the judge of which ideas become real. The equations can predict structures the universe never builds, can describe objects that geometry permits but thermodynamics forbids, can show us paths not taken and possibilities left unrealized. And there's something peaceful in that, isn't there? The universe has made choices about what exists and what doesn't, and we can rest in those choices, can explore them with curiosity rather than anxiety, can learn from both presence and absence. Black holes exist and teach us about gravity's strength. White holes don't exist and teach us about time's arrow, about why the universe ages in one direction, about how mathematics and physics relate. So let white holes remain where they are, in the equations, in our thoughts, in the quiet spaces between what is and what could be. They've served us well tonight, guiding us through questions about time and causality, about symmetry and thermodynamics, about why nature chooses the solutions it does from the space of mathematical possibility. Sleep well, knowing that the universe is both stranger and more orderly than we imagine. Strange enough to permit white holes in mathematics, orderly enough to exclude them from reality. Rest in that balance, that tension between possibility and actuality, between what equations allow and what nature implements. Until next time, Night Wanderer. May your dreams be filled with impossible objects and profound symmetries, with questions worth asking even if answers remain elusive, with the quiet wonder of a universe that keeps some possibilities forever theoretical, forever beautiful, forever just beyond the edge of what is real. Good night.